So this is really a standard problem. It's in every physics class at this level, and it's in the same chapter. The problem breaks up into two parts. This first part, when the bullet strikes a block and embeds itself in it, is inelastic collision. That means that the kinetic energy is not conserved in this collision. The kinetic energy is not the same before and after the collision, because whenever there's any deformation in the collision, as there often is, automobiles for instance, the kinetic energy of the collision is getting used up, in this case boring a hole in the block and heating up the block. Generates a lot of heat. So an elastic collision, when the kinetic energy is conserved, doesn't generate any heat. Okay, but momentum is still conserved because this is a collision, and the external forces are all negligible compared to the forces being exerted between the bullet and the block. Um, and this collision here also is assumed to take place very rapidly. So there's no motion of the block until after the collision is over. Okay, but momentum is conserved. So that means that the initial momentum, which is so this is the first part, part A, I guess, A. The initial momentum is that of the bullet alone because the block before the collision is not moving. So the initial momentum, I'll call it the INI. The initial momentum is the mass of the bullet, 0.01 kilograms. That's that's 10 grams. That's a normal bullet. 0.01 kilograms, once again, leaving off the units, times the velocity of the bullet. That's what we're looking for. I'll call it V sub B. Unfortunately, that would also be V sub block, but that's all right. Small b, whatever. Now, that's got to equal the final momentum of the, after the collision, the bullet's embedded in the block. And so the mass after the collision, this thing is going to set off with some velocity. That's this velocity right here that it's going to set off in part B. And so the mass of the bullet in the block is just what you think. It's 2.5 kilograms. That's the block. Plus 0.01 kilograms. That's the bullet. And this is going to be this. We'll call it big V. That's the velocity of the bullet in the block after the collision. That's the velocity that's going to be starting out part B. We'll call it big V. And in this part, there's an external force of gravity, so momentum is not conserved in the second part. So it's kind of interesting. In the first part of the problem, momentum is conserved, but kinetic energy isn't. In the second part of the problem, momentum is not conserved, but the kinetic plus potential energy is conserved. So afterwards, this thing in part B, this bullet and block together have a certain amount of kinetic energy, and as its pendulum swings out, that kinetic energy turns into the potential energy of the bullet and the block until it reaches a point where it's the highest point where it's all potential energy. So I'm going to use, for part B, I'm going to use the equations in last chapter. So the kinetic, I'm not going to write out the whole equations. I'm just going to take the kinetic energy initially is equal to the gravitational potential energy finally. That's what would come out of that. So I'm going to have 1/2 for part B. I'm going to have 1/2 times 2.51. That's the mass of the bullet and block together. 1/2 m times v squared. And that's going to equal the gravitational potential energy finally, which is going to be mgy. So 2.51 kilograms times 9.8 times the final y. And the final y, if I'm looking at this right, it looks like it rose to a height of 0.65 meters. Okay, these 2.51s cancel. That's nice. So this is going to, I'm going to solve part B first to find a numerical answer. And that's how things go sometimes in life. You have to do the second part first. And so it looks to me like V is going to be 9.8 times 0.65 divided by 1/2. Well, it's the same as multiplying by 2, so I'll just multiply by 2. And then I got to take the square root of it. Times 2. This is times. Okay, so now I'm going to pull out my contraption here and turn it on and take a square root. And 9.8 times 0.65 times 2. Close up that little square root, and I get 3.57 meters per second. That's the velocity of the bullet in the block after the collision. Now I can go back to part A and find the velocity of the bullet. Doing a little math, this is 2.51 and this is 3.57, and I got to divide by 0.01. So I get 2.51 over 0.01 times 3.57. And that'll all be in meters per second at the end of the day. So I got to take 3.57 times 2.51 equals that, and divided by 0.01. And I get 896 meters per second, rounding off. 896 meters per second. And that's how that goes. A very nice problem. I did this example last time. This was quite a chore, this collisions in 2 dimensions. Of course, you've got to, it's going to be twice as much work as your Chapter 7 homework, and see what kind of questions they ask. I might do a couple of these. So there's Wiley Plus. There's the Wiley Plus homepage. Let's go to the student view. Assignments. Let's look at Chapter 7. Let's, when's that due? April 9th. All right, time to get started on those. So let's try problem number 17. Just look at it and see what it says. A 2.6 kilogram cart is rolling along a frictional horizontal track towards a 1.7 kilogram cart that's initially at rest. The two carts are loaded with strong magnets that cause them to attract one another. Thus, the speed of each cart increases. At a certain instant before the carts collide, the first cart's velocity is 3.9 meters per second. That must be to the right, that's what plus means. And the second cart's velocity is minus 2.9 meters per second. What's the total momentum of the two cars at this instant? Okay. MV is momentum. P is its symbol. It's a vector. In this case, it's just going to be in one direction. let's see. First cart is 2.6 kilograms. And it's moving at 3.9 meters per second. Tablet is acting up on me here. Oh. 2.6 kilograms. Uh, 3.9 meters per second. The second one is got a mass of 1.7 kilograms and a speed of negative 2.9 meters per second. Well, that is what it is. I believe it's going to be positive, right? Because 2.6 and 3.9 are each bigger than 1.7. Yeah, this is going to be about twice as big as this. So it's going to be positive. What's the velocity of the first cart when the second cart was still at rest? Well, there's nothing but internal forces here. So whatever this number is, well, I guess we need to find it for part B. So let's turn it on. 2.6 times 3.9 equals that plus 1.7 times negative 2.9, and I get 5.21 kilogram meters per second straight. Meters per second. Okay, let's put that in. 5.21, make sure it works. See if these equations I'm telling you are true. Kilogram meters per second or Newton seconds. There's the units of momentum. And then for part B, the 2.6 kilogram cart was moving a little slower, I think, probably. Or maybe a little faster. The 2.6 kilogram cart, we'll find out in a minute, is moving with some velocity. The other cart's not moving, so it doesn't have any momentum before the magnets started attracting each other. And this momentum has to be the same if we can ignore external forces. The external forces here are gravity. We can ignore that because it's being canceled out by the normal force on this horizontal table or horizontal track. We're assuming that the track is frictionless right here, and that's another external force that's not going to affect momentum. So that takes care of all of them, I think. Except you have the internal forces, of which the attraction of the magnet is an internal force that's acting between the two cars. So we just calculate what the velocity is. Take 5.21 and divide it by 2.6. Oops, tablet disappeared again. So here's the momentum of the Here's the momentum of the cart before the attraction started to occur. The other one's at rest. And there's a total momentum, which has to be the same. So I take 5.21 over 2.6. And I get 2. And the units would be meters per second. There it is. All right, see if those equations worked. Yay! Let's do one more here. A projectile is fired, embeds itself in a target. The target is initially stationary. The target with the projectile flies off after being struck. What percentage of the projectile's kinetic energy does the target with a projectile in it carry off after being struck? Okay, we don't have very many numbers here. So this is number 35. So I'm not going to work this all the way down. I'm just going to talk about it a little bit. What percentage of the projectile's incident? So we have Mr. Projectile here, and then here's the target. The target's initially at rest, and I'm just going to call this initial velocity of the projectile VI. They don't tell me what it is. So I'm going to have a lot of symbols in this. They do tell me what the mass of the projectile is and the mass of the target. So this is 0.129 kilograms. And the target's a lot heavier. It's 1.8 kilograms. And turn this tablet around here. Now, projectile's incident kinetic energy. That's going to be, I'll call that kinetic energy initial. That's equal to 1/2 times 0.129 kilograms times V initial squared. It's from last chapter. Okay, after the collision, this is before the collision. After the collision, we have this target with the projectile in it. It's got a mass of 1.8 plus 1.129, and it's moving off with some velocity. Once again, I don't know. I don't know what the initial velocity of the projectile was. And so quite similarly, I don't know what the final velocity of this thing is, but I do know its mass. It's 1.8 plus 0.129. I'm going to add those together, and I would get 1.929. But momentum has to be conserved in this collision. So I'm going to say that the mass of the projectile, 0.129, times the incident velocity of the projectile, same VI is up in this equation, has got, that's the momentum before the collision, has to be equal to 1.929 times the velocity of the, I'm calling capital V, the velocity of the projectile and target after the collision. Okay, lots of unknowns here. What's the final kinetic energy? Well, that's this due to this motion of this projectile and target stuck together. So that is 1/2 times 1.929, that's the mass after the collision, times this velocity squared. Okay, more stuff I don't know. But what are they asking me for? What is the question? They want to know what is the ratio, what percentage of the projectile's incident kinetic energy does the target carry off with the projectile, carry off after being struck? So they're asking me for the ratio of the incident kinetic energy, because what fraction of the incident? What fraction? Oh, got to read this carefully. What percentage of the projectile's incident kinetic energy does a target carry off? So they're asking me for the ratio of the final kinetic energy. That's the amount of kinetic energy that the projectile carries off, divided by the initial kinetic energy. That's the amount of energy that the projectile had before the collision. Okay. Well, a lot of stuff's going to cancel here. So I'm going to have 1/2 in the numerator and denominator. That's going to go away. Upstairs, I'm going to have 1.929 kilograms. And downstairs, I'm going to have 0.129. And upstairs, I'm going to have v squared, the velocity afterwards, over the v squared. And I can find that number from this equation right here, the conservation of momentum. Big V over little v is equal to 0.129 divided by 1.929. So this is going to equal 1.929 over 0.129 times 0.129 squared divided by 1.929 squared. Well, one of these cancels. One of these cancels. And I get 0.129 over 1.929. Gee, I wonder if this works. Let's grab my contraption here, check it out. I get 0.129 divided by 1.929. And I get 6%, 0.067. What units do I have here? Percent? No. They want this in percentage. Yeah, what percentage, right. So I need to go back to my contraption here. That would be 6.7% if I multiplied by 100. Why is this red? See if that works. Yay!